Hello everyone, my name is Rong Chaodong and I'm from Fudan University in Shanghai. It's a great pleasure to be here and present our latest research in dynamic binary translation. The title of our paper is More with Less, Deriving More Translation Rules with Less Training Data for DBTs using Parameterization. Here is a brief outline of my talk. I will first give some background and motivation of our work, and then explain our learning-based parameterization approach in details, followed by some experimental results and conclusion. Dynamic binary translation, DBT for short, is a general technique to translate guessed binaries run on a host machine with a different or the same instruction set architecture. It's a key enabling technology for many important application areas, such as system virtualization and for software development when new hardware is still under development. DBT is driven by translation rules that translate a guessed binary code sequence to a host binary code sequence. Each translation rule is consists of two parts, a guessed instruction sequence and its corresponding semantically equivalent host instruction sequence. For example, the ARM instruction on the left can be translated to the semantically equivalent x86 instruction on the right. To support the translation from multiple guessed ISRs to multiple host ISRs, a DBT usually uses an intermediate representation to facilitate such translation. This approach has several limitations though. Firstly, because the translation has to go through the IR instead of binary to binary, its translation overhead is much higher. It also can cause a significant code expansion because each guessed instruction may be translated into several IR instructions, and each of which can be further translated into multiple host instructions. It can also limit the ISR-specific binary optimization because IR is ISR independent. Learning-based translation is a novel approach proposed recently. It uses source code in a training set to generate semantically equivalent translation rules. For example, it first compares a source code to both ARM and x86 binaries, and the instruction sequence of ARM and x86 binaries from the same source statement are extracted as the translation rules cadet. Their semantic equivalence is then verified by symbolic execution with the SMT solver. The rule generation through such a learning process can be done automatically without going through IR, which allows it to generate a very high quantity host binary code. However, this approach has some significant limitations too. Firstly, its dynamic coverage is often limited, which means a substantial amount of guessed binaries can't be covered by the generated rules and has to go through emulation or through conventional translation process. Using Spec 2006 as a test case, the dynamic coverage is only around 69.7%. Another issue is that the number of rules that can be harvested saturated very quickly. Using Spec 2006 as an example again, very few new rules can be generated after around 6 programs, which means we need a very large and diverse source code base as a training set to generate a comprehensive set of translation rules in order to improve coverage. To mitigate such limitations, we take advantage of a well-structured format in most ISRs in our approach. Most instruction formats has two major components, opcode and operand, which can have multiple addressing modes. For example, all ALU-related instructions, such as and AND instructions in ARM, has a similar format of OP, R0, R0, R1. For AND instruction, its operand can have different addressing modes, such as register or constant. It implies that if we have learned the rule for the AND instruction, we can apply the rule to other ALU-related instructions as well, even if they have not appeared in our training set yet. The key here is to abstract the opcode and the operand components and apply similar translation rules to those opcodes and operand of the same type. We call this abstraction process on opcodes and operand, which is parameterization. That is, we parameterize the opcode and operand components in the translation rule we have learned. So we can extend them to those rules we not learned yet but are similar. In this way, we can expand a small set of learned rules to a large set of translation rules, even if they are not learned yet. This can also drastically cut down the training set size need to produce a comprehensive set of translation rules. Here, we give a little more details on parameterization process. The opcode parameterization will be performed at first. We group all opcodes into 5 types. It include ALU type, memory operation types which include move, load, and store types, compare type, and other type. In this example, the learned translation rule on the left that translates a sequence of and store instruction in ARM to AND-L and move-L instruction in x86 will parameterize them into OP1 for AND and OP2 for store because AND is one of ALU type and store is one of memory operation type. The addressing mode parameterization comes next. In this example, the OP1 instruction, the third operand will be parameterized as OPRD, and in the OP2 instruction, the second one will be parameterized as MIME. In this case, those addressing modes include register, memory operand, constant, and others. During the parameterization, there are some constraints that require further attention. In opcode parameterization, there is a constraint that is related to commutativity of the opcode. For example, AND operation is commutative while sub operation is not. In this example, the AND instruction performs R0 equal R1 plus R0. The sub instruction performs R0 equal R1 minus R0. After opcode parameterization, we will have R0 equal R0 plus R1, which is the reverse of R1 plus R0, and the result is correct. But if we apply this to sub instruction, we will have R0 equal R0 minus R1, which is wrong because sub instruction is non-commutative. We can't reverse R0 and R1. In our implementation, if an opcode is non-commutative, it will not be parameterized, but will have its own translation rule. In the addressing mode parameterization, there are also some constraints. For example, ARM treats the program counter as a regular register that can be modified, where x86 can modify the program counter. In this case, we use a general purpose register to replace program counter, such as register 0 in this example. And PCR is a pseudocode which is used to request the register 0 from QEMU. For other relevant constraints, please check section 4 of the paper for more details. Those constraints will be kept as part of the translation rule and will be checked at runtime when it's applied. In the binary translation process and runtime, those parameterized rules will be used to translate the guest code to the host code. When a guest binary sequence matches a parameterized rule, this rule will be instantiated first. The instantiation means to restore the parameterized symbolic representation, such as OP1 and OPRD, back to their original values. In this example, the guest instruction performs a bitwise AND operation, and it can match by the parameterized rule shown here. The parameterized opcode OP1 will be instantiated to the AND opcode in the guest instruction and AND-L opcode in the host instruction. The operand reg and OPRD will be instantiated to their corresponding values and will. During the instantiation, the constraints mentioned earlier will be checked to guarantee the correctness. The condition code also need to be emulated to maintain correctness. In our implementation, we use a technique called condition flag delegation to optimize condition code emulation. instead of use of pure software condition code emulation like in QMU. The details are in the paper. This is the workflow of our parameterization approach. Through parameterization, we can derive more effective translation rules with a much smaller training set. It can significantly improve the coverage and the performance. In the workflow, we first generate the parameterized rules through opcode and operand parameterization. Some constraints are added if needed to guarantee the semantic equivalence when the translation rules are applied. During the translation process, we use instantiation and constraint checking to generate a host code. And at the same time, we use condition flag delegation to optimize condition code emulation. We implied our scheme on QMU 4.1, a state-of-the-art retargetable dynamic binary translation platform. We also use the 12 benchmark programs in Spec 2006 as our test set. We use 11 of them as a training set, and the harvest parameterized translation rule is then applied to the remaining one. We compared the code quality of our translated code with those translated by QMU. As the execution time of a program is directly linked to the number of instructions executed at runtime, we define the code quality as a ratio between the number of translated host instructions to the number of guest instructions. That is, the fewer translated host instructions needed to emulate the guest instruction, the better code quality. As ARM is a RISC architecture where x86 is a CISC architecture, we expect to have fewer x86 host instructions than the ARM guest instructions. Our measurements show that, on average, for each guest ARM instruction, it's translated by only 0.97 x86 instructions with our parameterized rules, as opposite to 3.49 instructions in QMU, because it has to go through the IR. We also measure the dynamic coverage and the performance of our approach. In this figure, we show the dynamic coverage of each programs. The vertical axis is the dynamic coverage, which is the percentage of the total host instructions executed that are translated from the parameterized rule. Those instructions that are not covered need to be either emulated or go through the binary translation process of QMU. As mentioned earlier, without parameterization, the coverage is around 69.7 using existing Selenium-based approach. With only opcode parameterization, the overall coverage is increased from 69.7 to 79.8%. After adding addressing mode parameterization, the overall coverage is increased from 79.8 to 87%. And after condition flag delegation, the overall coverage is increased from 87% to 95.5%. The performance also improves quite substantially. The baseline is the existing Selenium-based approach without parameterization. With only opcode parameterization, the performance increased by 1.09. After adding addressing mode parameterization, the performance increased to 1.17. And after condition flag delegation, the performance increased to 1.24. In conclusion, let's summarize our work here. We propose a parameterized Selenium-based approach for DBT. It can achieve a much higher dynamic coverage with a smaller training set size. Experimental results on QMU 4.1 show that it can outperform state-of-the-art Selenium-based approach by 1.24. And we have opened our source code at the follow link in the GitHub. Thanks.